Ahoy hoy, it's Mr. Nickerson here, and I'm here today to teach you a little bit about solving systems of equations by graphing. Right now, if you pull out the note sheet that you received at the end of class, and we'll get started. Solving linear systems by graphing. Well, first we're going to talk about what a linear system is. A system of linear equations, or sometimes known as a linear system, consists of two or more linear equations in the same variable. An example here would be x plus y equals 1 and negative 2x plus y equals negative 5. This time we have two equations and they both contain the same variables x and y. Most commonly in this course we'll see two equations. Could we see 3 or 4 in the future courses? Absolutely. But for right now we're going to focus on just systems with two equations. Let's scroll down a little bit. You're going to learn three ways to solve systems of equations. The first way we'll learn is by graphing. We're going to use skills that you've previously learned in Algebra 1 Part 1. To solve by graphing, it's really three steps. The first step being that we have to graph the two lines. To graph lines, we've got several options, and the first option, probably the best one for most of you, is going to be using slope-intercept form. Looking at our first equation, it's not in slope-intercept form, so to get it in slope-intercept form, we're going to subtract x from both sides, get y equals negative x plus 1, and that one's all set. It's in slope-intercept. The other equation, not in slope-intercept either, so we got to get it there. Add 2x to both sides. And we get y equals 2x minus 5. Now that we have those in slope-intercept form, we're able to graph them. So I'm going to graph my first equation, y equals negative x plus 1. We'll start at 1, and then we'll apply our slope down 1 over 1. Down 1 over 1. Usually, you learned in your previous class that only 2 points are needed to make a line. But due to the system of equations, it's best to extend your line several extra points. So right now I only have 4. I'd probably like to have some more continue. So we can continue these here. And that might be ample for now. Let's go to our second equation. Y equals positive 2x minus 5. Well, start down at negative 5. And we graph that equation. Slopes of positive 2 over 1, up 2 over 1, up 2 over 1. Something special just happened. Magic's in the air. Okay? We want to find, what we'll look for in a second, is the point of intersection. We just found that. So I'm going to make sure I emphasize that point a little bit larger. I'm just going to continue for a couple more points. Once we've successfully graphed, we want to look for the point of intersection. So we want to write the ordered pair where the two lines intersect. I'll make an empty bracket. And this time my ordered pair is at over 2, down 1. So positive 2, negative 1. Once you have that point, you can take a ruler, using a ruler or a straight edge, and you can connect your lines. Always want to use a ruler, folks, when you're connecting your lines. You never want to do them by hand. Always use a ruler. Okay? The last step, very important step, is the check step. We're going to take our ordered pair where the two lines intersect, and if that's truly the answer, we should be able to take this point and plug it into both equations and get true answers. We could either plug it into the originals or we could plug it into our rewritten equations. For right now, I'll use the rewritten equations. So let's plug it in. Where I see y, I replace my negative 1. Where I see x, I replace with my 2. And now we simplify. Is negative 2 plus 1 equal to negative 1? Well, would you look at that? It is. We continue. Plug it in over here for a check. Plug it in, -1 for y. 2 times 2 minus 5. Well, 2 times 2, +4, minus 5. Would you look at that? It certainly checks out. And we just completed our first problem by graphing systems of inequations. All right, let's take a look at example 2. On the second problem, we start by graphing the two equations. As you can see, the forms are not in slope-intercept form to begin with, both equations, so we need to rewrite them. First equation rewrites to y equals -x plus 2. And then the second equation took a little more work, but it rewrites to y equals x over 2 plus 5. We graph those two lines, and then we can find our point of intersection. Once you do that, this is the part where some people might get confused. You graph this line here, which is y equals -x plus 2, pretty easily. But the second equation, y equals x over 2 plus 5, you start up at 5, you go up 1 over 2, up 1 over 2, up 1 over 2. And it's not going to hit up here. You know it's going to hit somewhere over here where they intersect. So we apply our slope down 1 over 2, so it falls in line, and then we can find our point. Once we find our 2 points, we're able to check them in both equations, and then finally, don't forget, use a ruler and connect the lines. All right, on the second example on the second page, you first need to rewrite your equations in slope-intercept form, and you should get the two boxed equations, y equals -4/3 x, and y equals -2x minus 2. After that, we graph both lines, graphing the first equation, start at the origin, down 4 over 3. I continue that the other way by going up 4 and over 3. My second equation, y equals -2x minus 2, start at -2, go down 2 over 1, down 2 over 1. And some of you might be saying on this problem, it doesn't look like they're going to hit this way. You're right. It's not going to happen in the fourth quadrant. Where it's going to happen? Well, it's got to happen up here in quadrant 2. So we got to be comfortable with that concept of slope and be able to apply it as well in both directions. So we can go up 2 over 1, up 2 over 1, up 2 over 1, and then we find that point at -3, 4. Check it out. It does check out for both. Once we know it checks, then you can use your rulers to connect the points. All right, let's talk about the third page. The steps don't change, the directions are the exact same, but something a little bit different is going to happen this time. Let's first solve these for slope-intercept form. -3x and then divide by 2. So we got y equals -3 over 2x plus 3. Let's go to our second equation. The second one. Well, we're going to subtract 3x again. And then we'll divide by 2. Excuse me. You're going to notice something about these equations compared to all the other problems we've done. Hopefully something that jumps right out at you is the slopes. The slopes on both of these equations are the exact same, but they have different y-intercepts. Same slope, different y-intercepts. Well, hopefully you remember what that's called from before. That's called parallel lines. And what do we know about parallel lines? Parallel lines never intersect. So when we graph these, we'll still graph them respectively, but we know the answer right now for the point of intersection. There is none. How do we write that? No solution. When you have a no solution answer, can you check it? There's no check needed. There's no answer that's going to check out in both of these. You can still graph them. So let's do that real quick. And we only need 2 points to make a line, remember, so we don't have to extend these ones. We know it doesn't connect, so we're just going to connect them. And that problem's done. Let's scroll down now to the next example. Next one that we have here, same steps. So we're going to graph it. So we got to get this in slope-intercept form. And this one's already in slope-intercept form. Hopefully something else jumps right out at you. Okay? These are the exact same equations. So hopefully you're asking yourself, well, Mr. Nickerson, if I have the exact same equation, and I graph it, and I graph the exact same equation, how many lines are going to be on that graph? Only one. These are the same. So it's only going to be one graph. And a lot of you might be thinking, well, we just talked about no solution on the previous example, and everything else we've learned so far in algebra, when there's a no solution, there's an all real numbers. Good thought process. But, since we're dealing with a system of equations, we have ordered pairs. So the concept of all real numbers doesn't work right now. There's a different terminology for when this happens. What this is known as is infinitely many solutions. And the difference between infinitely many solutions and all real numbers is that when we graph this line, so let's do that. Positive 2 down 2 over 1. We got 2 points. We can connect it. Is when we have infinitely many, what that means is any one of those points on the line would work in the equations. But a line goes on infinitely. So they call it infinitely many because there's an answer right here. This point, 0, 2, that works. Or 1, 0, that works. This point right here, 2, negative 2, that would work. Any point on that line. And since the line goes on forever, it's going to be that there's infinitely many solutions. When you go to check it, no need to check it infinitely many. We're all done. Hopefully on example 3 here, or the first example on the last page, you came up that they were the same equation, and since they were the same equation, only one line, infinitely many. And hopefully for problem number 4, you notice that once you solve both equations in the slope-intercept form, same slope, different y-intercept, those lines are parallel. When the lines are parallel, no solution's your answer. Don't have one, can't check it, and that's all. That concludes today's lesson, and we'll see you tomorrow in class.